Greetings and welcome to Unit 1, Lesson 4. We're going to solve some trig equations. So by the end of this lesson, and not necessarily this video is just going to deal with the first part of the lesson. We want to know what the different techniques are to solve trigonometric equations, and we'll use them to solve real-life problems. So what does it mean to solve a trig equation? And you're just going to take the algebra skills that you have learned throughout your career, and you're just going to apply them in a new context. So we're always trying to solve for x. Now we are trying to solve for the sine of x. We need to isolate that. So using our algebra skills, I'm going to add 1 to both sides, and that gives me 2 sine x equals 1. And then I'm going to divide both sides by 2 and get the sine of x is equal to 1/2. So now I have isolated the sine of x. But what does this mean? We don't want to cross through it. Let's try the highlighter. Okay, fantastic. What does this mean? Well, it means if I look at the graph, if I graph the sine of x, which you see in blue, and 1/2 in red, I want to know where they intersect. So when I am asking what is the solution, and then I ask a following question of what is the solution in the interval just from 0 to 2 pi, let's talk about the main solution first. The main solution is an infinite amount. Notice this is a place where 1/2 intersects the sine curve. Here's a place where it intersects. I have a place over here and here. And because sine keeps going in, has a period of 2 pi, there are going to be places over here where it's going to intersect again. So the solution has to account for this infinite amount of points. How do I get to that general solution? Let's look at what the solutions are just in the interval from 0 to 2 pi or in one revolution of my unit circle. So again, an equation wants every possible solution that makes the equation true. So if I look for y coordinates that are 1/2, I see a y coordinate here at the pi over 6 location, and I see another positive 1/2 in the y coordinate as a y coordinate here at 5 pi over 6. So if I was just asking for what is the solution from 0 to 2 pi, my final answer would be pi over 6 and 5 pi over 6. But it's also every single revolution that also gets me to 5 pi over 6. So every revolution this way, and then every revolution in the opposite direction, and the same is true for 5 pi over 6. So how do I denote that algebraically? I denote it by saying x is equal to pi over 6, which is an angle in the interval from 0 to 2 pi plus 2 pi n, or 2n pi. That is saying every multiple of 2 pi added to the pi over 6 will work. All the coterminal angles to pi over 6. Also 5 pi over 6 plus 2n pi will also work. Again, the 2n pi denoting all of the angles coterminal to 5 pi over 6. So the next 5 examples that I'm going to present to you are going to exemplify the strategies you might need to use to solve a trig equations. To show collecting like terms, you can refer to example 1. Extracting square roots will be shown in example 2. Factoring and applying quadratic type strategies will be shown in example 3. Factoring and rewriting with a single trigonometric function will be shown in example 4. And example 5 will be will show squaring and converting to quadratic type. So let's do example 1. On example 1, we see the sine of x plus 1 is equal to the opposite of sine x. Life is good. This problem isn't so bad because everything is in terms of a single trigonometric function, or the sine. And there's no squares, there's no powers, pretty easy. All we have to do is collect like terms on a problem like this. So what does that mean? I'm going to go ahead and add sine x to both sides. That would yield 2 sine x plus 1 equals 0. I'm going to subtract 1 from both sides, giving me 2 sine x equals negative 1. Then I have the sine of x is equal to negative 1/2 after I divide by 2. Now that I have isolated the sine of x equals negative 1/2, I'm going to use my unit circle to find places where I see a y coordinate is negative 1/2. That is occurring at 7 pi over 6 and at 11 pi over 6. But the directions are to solve the equations. That means I have to count for every possible solution, and therefore every angle coterminal with 7 pi over 6 and 11 pi over 6 is going to work. So my final answer is going to be 7 pi over 6 plus 2n pi, recalling that 2n pi accounts for the coterminal angles with 7 pi over 6 that are also solutions. And x equals 11 pi over 6 plus 2n pi. Again, I'm adding 2n pi to account for all the angles coterminal. So in this problem, 3 cotangent squared x minus 1 equals 0. I want to isolate the cotangent squared of x before I can do anything else. So I'm going to go ahead and add 1 to both sides, which is going to yield 3 cotangent squared x equals 1. Next, I'm going to divide both sides by 3, yielding cotangent squared x equals 1/3. So the extracting square roots comes in when I need to get the cotangent squared x to regular cotangent. So I'm going to go ahead and square root both sides. But remember, when you square root both sides, you have to account for all solutions. And so I end up with plus or minus 1 over root 3. Or you can rationalize it, but I'll show you how that's not necessary. So now that I've got the cotangent of x isolated, I am going to go ahead and look on the unit circle for places where an x coordinate over a y coordinate, which is the definition of cotangent, is 1 over root 3. So by process of elimination, I know none of my quadrantal angles are going to work, because if I take any combination of x's and y's there, I'm going to get zeros, ones, negative ones, and undefined. I can also eliminate anything that has to do with the 45-degree angles, because root 2 over 2 over root 2 over 2 is going to get me 1. So now let me go to pi over 6. If I take root 3 over 2 and divide that all by 1/2, the denominator of 2's are going to cancel, and that's going to leave me with root 3. That's not 1 over root 3. So now I can eliminate any of the points that have a root 3 or a negative root 3 over 2 in the x place. So by process of elimination, I now know I've got 4 places where I'm going to get 1 over root 3. At pi over 3, I'm going to get a positive 1 over root 3. At 2 pi over 3, I'm going to get a negative 1 over root 3. At 4 pi over 3, I'm going to have a negative negative, so that's going to be a positive 1 over root 3. And at 11, you know what, I crossed out the wrong one from earlier. It should be this area. At 5 pi over 3, I'm going to get negative 1 over root 3. Now, when you look at my answer, you might be thinking, Nap, you're off your rocker. First of all, I have to account for all of the possible solutions. So why didn't you write pi over 3 plus 2n pi? And why didn't you write 2 pi over 3 plus 2n pi? And why didn't you write 4 pi over 3 plus 2n pi? Or 5 pi over 3 over 2n pi? That's because if you recall, cotangent has a period that occurs every pi radians, not 2 pi. So if I consider pi over 3, and I add pi to it, which in thirds would be 3 pi over 3, it's going to yield 4 pi over 3. If I take 2 pi over 3 and add pi, which cotangent is pi periodic, so if I add pi, which in thirds is 3 pi over 3, it yields 5 pi over 3. So it's unnecessary to really list all 4 and then add 2 pi n to all of them. I can really just add the pi over 3, the 2 pi over 3, and that's going to take care of not only coterminal angles with pi over 3 and 2 pi over 3, but also coterminal angles with 4 pi over 3 and 5 pi over 3. Welcome to example 3. I wanted to show you this problem or this equation because we're going to use some quadratic type strategies to find the solutions. I have changed up the directions for you a little bit. Instead of finding every solution or the general case, I'm asking you to find all the solutions in the interval from 0 to 2 pi, which means I just want all of the solutions within one revolution of the unit circle. So these questions, for example 3 and for example 4 and 5, it's going to be these directions. We aren't going to need to worry about adding a 2 pi n or adding an n pi to our answers. Our answers will be pretty concrete angles within one revolution of the unit circle. All right, so if you bear with me here, let me show you a parallel problem before I delve into this trig equation. Let me show you 2x squared plus x minus 1 equals 0. It's a very similar setup. It's a quadratic, you know and you love. I can solve this by using my factoring skills that I've acquired through my algebra lessons. So I have 2x squared plus x minus 1 equals 0. There's no GCFs, and this is going to factor from the trinomial into two linear factors, 2x minus 1 and x plus 1. If I use the zero product property and set each of those factors equal to 0, I would yield 2x minus 1 equals 0 and x plus 1 equals 0. For the 2x minus 1 equals 0, I'm going to add 1 to both sides and divide by 2. For x plus 1 equals 0, I'm going to subtract 1 from both sides, and I do have a typo right there. That should be a negative 1. And so my solutions to this quadratic would be 1/2 and negative 1. I'm going to argue that if you thought that was easy, solving example 3, 2 cosine squared x plus cosine x minus 1 equals 0 is not going to be any different. It's the same format. Instead of x's, I have cosine x's. So when I go to factor this, I have 2 cosine x minus 1 times cosine x plus 1 equals 0. Why does this work? Because if I use the distributive property, or FOIL, I would get 2 cosine squared x. My outer terms would yield plus 2 cosine x. My inner term would yield a negative cosine x. And my last would yield a minus 1. So when I combine the like terms in the middle, I get exactly the equation I started with. So now I'm just going to set each of those factors equal to 0 using the zero product property, just like I did with the regular quadratic. So let's look at 2 cosine x minus 1. 2 cosine x minus 1 equals 0. I would add 1 to both sides, then divide by 2. And then I need to go to the unit circle and find places where I have an x coordinate that is 1/2. So that is going to occur here at pi over 3, and it's going to occur again here at 5 pi over 3. Again, because this is not asking for a general solution, it's asking for all of the solutions in the interval from 0 to 2 pi. I get those solutions from that part of the equation. But I'm not done. I also have to set the cosine x plus 1 also equal to 0. Then I'm going to subtract 1 from both sides. And now I have to find a cosine x, or an x coordinate on the unit circle that's equal to negative 1. And that is going to occur here at pi. So my final answer to this problem is pi over 3, 5 pi over 3, and pi. And here we are. We are at example 4. The reason I'm presenting this problem is to show you how you can rewrite an equation in single trig form, and we'll also do some simple factoring. So I see 2 sine squared x equals 2 plus cosine x. Here's what's bugging me. I see a sine squared x, I see a cosine. First of all, they're not the same powers, and furthermore, they are not the same trig function. So in order to deal with this, you need to convert either the sine squared of x into a cosine or the cosine of x into a sine. When I think about all the identities we've learned so far, none of the fundamental identities really do anything with a single cosine of x to convert that into some kind of expression using sine. But I've got the Pythagorean identities to help me with the sine squared of x to convert that into cosine. So recall that sine squared of x plus cosine squared x equals 1. What I can do is solve for the sine squared of x, so that sine squared of x equals 1 minus cosine squared x. So now I'm going to substitute 1 minus cosine squared of x for the sine squared of x, yielding me with 2 times 1 minus cosine squared x equals 2 plus cosine x. And even though it looks like I kind of have a little bit of a mess, at least I have my equation all within one single trig function. So next I'm going to use the distributive property and distribute the 2. So I'm going to have 2 minus 2 cosine squared x equals 2 plus cosine x. Now I need to get everything to one side. This has got a quadratic type strategy to it. So I need it to equal 0 before I can figure out what to do. So when I'm going to actually take the 2 minus 2 cosine squared x and move it to the right. So the 2's are going to cancel, and I'm going to be left with a positive 2 cosine squared x plus cosine x. Please do not overlook the power of the GCF. A lot of times people are going to look for really complicated factoring, and the quadratic strategies come up a bit, and really good old GCF is what comes up all the time. They both share a cosine of x, so I pulled that out, leaving me with a 2 cosine x plus 1, and now I can use the zero product property. If I focus in on the cosine of x, that's going to equal 0. So I need to find places on the unit circle where the x value is 0, and that is going to occur here at pi over 2, and then again here at 3 pi over 2. And now I can focus on the other factor, which is 2 cosine x plus 1 equals 0. So I'm going to subtract 1 from both sides and then divide by 2. So I need to look for places on the unit circle where x is equal to negative 1/2. And I see that up here at 2 pi over 3 and down here at 4 pi over 3. And again, the directions were to find all of the solutions just within the interval from 0 to 2 pi. So my final answers are pi over 2, 3 pi over 2, 2 pi over 3, and 4 pi over 3. And we are almost done. We are on our last example of this video, cosine x plus 1 equals sine x. The purpose of this example is to show you about squaring and converting to quadratic type. I do not think, personally, when I look at this problem, that is very intuitive what to do. Here's what bothers me. First of all, I don't have the same trig function. But because there's no powers, I don't have any identities right now that is going to help me take cosine x and convert it into sine x. So I could maybe use the cofunction identities, but still that's really not going to help me a whole lot. I need to keep things in terms of a single x. So that's what bothers me. But don't forget that whatever you do to one side, you can do to the other. I could add 100 to both sides. It's a legal move. It might not help me, but it works. So here's what you want to try. Try squaring both sides. And I think you'll see why as we go through the problem. Because the only relationship I have at this point between the cosine and the sine is if there's some type of Pythagorean identity. So if I can get the cosine and or the sine to be a square, it's going to give me more to work with. So that's kind of the method to my madness there. So if I square both sides, which is a legal move, whatever I do to one side, I'm doing to the other. Please remember on the left, you need to write that twice and distribute. So when I do that, I get cosine squared x plus 2 cosine x plus 1. So again, if you're wondering, where in the heck did not get that on the left? I have to write it twice. I have to write cosine of x plus 1. I know this is kind of sloppy. And then I have the cosine of x plus 1. And I'm going to spare you from doing this on the video because by now you've seen me do this in a previous problem. I'm going to first outer interlast that or use the distributive property, however you think about that, to yield cosine squared x plus 2 cosine x plus 1. And then when I square the sine of x, I can write it as the sine squared of x. Now, if I notice on the left, I've got a lot more cosines going on. I've got this single cosine right here going on. So instead of trying to get the cosines in terms of sine, I'm going to convert the sine squared x into cosine squared. So from a previous problem, we know that the sine squared of x from a Pythagorean identity is 1 minus the cosine squared of x. Next, I'm going to move everything to one side. So I'm going to subtract 1 from both sides and add cosine squared of x to both sides, yielding me 2 cosine squared x plus 2 cosine x. Again, if you're wondering, what in the heck do I do now? Factor. It's just a greatest common factor. Both terms share a 2 cosine x, and when I pull that out, I'm left with the cosine x plus 1. Next, I use the zero product property, and when I look at 2 cosine x equals 0 and divide by 2, I need to find x values that are 0. So again, that occurs at pi over 2 and at 3 pi over 2. When I look at the cosine x plus 1 equals 0, subtract 1, I am looking for where the cosine x is equal to negative 1, and that occurs at pi. So my final answers in the interval from 0 to 2 pi are pi over 2, 3 pi over 2, and pi. So you are ready to attack this learning opportunity number 1, which you will have the entire next period to work on, page 364, number 7 to 37 odd.